want to welcome everybody to the 18th lecture in Chemistry 51C here at UC Irvine. I'm David Van Vranken, and I just want to start off by honoring this amazing class that I have. You guys have been sticking with organic chemistry for at least 2 years through a general chemistry sequence, through organic chemistry classes. And we've arrived here in this coronavirus quarter where the campus is shut down. And I think we're making it work here using remote instruction. So I regret the fact that we don't have live lectures where I just feel like there's a lot more energy when we're all together. I'm not sure if I'm doing a good job recapturing that with our, by remotely delivering the lectures, but we're doing our best here. So stay engaged, keep working problems, keep coming to discussion sections, keep talking about chemistry during discussion sections. I feel like it's super critical to have the courage to talk about chemistry. You may be wrong sometimes. It doesn't stop me from saying things that are wrong. I just love talking about chemistry. And this is the environment to do it, right? We're supportive. I have to give you a grade on the exam, but I don't grade your discussion during discussion section. I love it when people talk about chemistry and are just willing to write anything down on a piece of paper. So keep doing it, and great job, everyone. What you're looking at here on the screen is Georgy Markov. He was a Bulgarian writer and a dissident that gained disfavor with the Bulgarian government, I think in the 1970s, maybe prior to that. And back then, when you became enemies in that kind of an environment with your government, they didn't just unfriend you online or assassinate your reputation online. They just killed you outright. And what you're seeing here is a model of an umbrella gun that was designed and used by the Soviet KGB to assassinate Georgy Markov. That's sad. But it gives us an opportunity to talk about chemistry, because this umbrella gun didn't fire a lead bullet. It fired a tiny, tiny, tiny pellet of a toxin called ricin. So let's talk about ricin. Ricin is a protein, extremely toxic. And over here on the left-hand side of the screen, I've got a cartoon rendering of ricin. It's composed of 2 protein chains stuck together. And this chain over here with the red cartoon backbone, that's nothing more than a delivery vehicle for bringing the ricin to human cells, tricking human cells to take this deadly yellow A chain into the cell where that ricin A chain can do its work. And the ricin A chain floats over to a ribosome, a human ribosome. That's this picture in the center, is the structure of a human ribosome. And that ricin A chain snuggles right here into a pocket that is normally occupied by a protein elongation factor. And that's where it does its job. Really cunning and really evil. It comes along and it catalyzes an SN1 reaction, an SN1 hydrolysis of a very specific bond in the human ribosome. It comes along to one of the nucleotides, number 4,324, to give you a sense for how selective it is. And that happens to be an adenylate residue with an adenine side chain or base hanging off of that. And this bond right here gets cut by ricin. There's an SN1 hydrolysis reaction where you protonate the adenine, and then the lone present in the oxygen push that out, and then water comes back in and replaces that. And when you remove that one adenine base from the entire ribosome turns into a worthless piece of molecular trash. Just complete molecular castration. Mother Nature is just devious and evil, and if I had my entire life, I could not design anything so toxic. And so, because once the ricin is done, it goes to the next ribosome and does exactly the same thing, not destroying the entire ribosome, but basically castrating each of the ribosomes inside the cell. And so that's what the Soviet agents shot him with, this little pellet of ricin, which is deadly. And what brings up this topic of ricin? Well, it turns out that you get ricin from the same place that you get castor oils. Ricin is isolated from castor beans. Recall that we talked about how if you squeeze castor beans, you get castor oil out of that. The oil will rise to the top, you skim it off, and that's what you use to synthesize white lithium grease, which is used as a common lubricant. But the protein part, the powder that's left over, you can purify that to make ricin. And ricin is a substance that's controlled by the Food and Drug Administration, just like other drugs and illegal substances. It's also regulated by the 1972 Biological Weapons Convention and the 1997 Chemical Weapons Convention. Extremely dangerous. And next time you're walking along that creek that runs alongside University Avenue next to the University of California, Irvine campus, you can find castor bean bushes all along that creek. Pick some of those little prickly pods and open them up, and each one is filled with a castor bean. Don't do stupid things with castor beans. It's not easy to isolate ricin from the raw protein powder, and it's not easily to inject that into people's bloodstream because it doesn't go through the human stomach. So just an interesting example of how really clever nature is. When we left off on Friday, we were talking about what people used to do before they had LDA, which is a really powerful base that you can use to deprotonate next to esters, next to amides, as long as there's not some other acidic functional group like an alcohol or an amide NH. You can use lithium diisopropylamide anion, that powerful lithium base, to deprotonate any ester at the alpha position. But before LDA, we didn't have those powerful bases. We had sodium ethoxide or potassium T-butoxide. And what people did is they would use 1,3-dicarbonyl compounds, which are so acidic that alkoxide bases can deprotonate those in high yield to make enolates in high yield, over 99%. You don't isolate the enolates, you use them immediately, but you can make a high proportion of your compound gets converted to enolates. And we used to use those back in the 1960s for making carbon-carbon bonds by doing SN2 reactions. Now, we have more ways to do that. Now, nowadays we have this option. So what do you do with those 1,3-dicarbonyls? Well, I think in the late 60s and 70s, they learned to make a class of drugs called barbiturates out of those, but generally you don't want 2 carbonyls. So there's a secret procedure for hydrolyzing off one of those 2 carbonyls. Whenever you have an ester group next to a ketone, next to another carboxylic acid, you can cleave that carbon-carbon bond by using hydrochloric acid and water and heat. And if you'd like, you can write 100 degrees here or a delta symbol. Now, these conditions are used for generally hydrolyzing esters, so both of these groups are initially converted into carboxylic acid. Let me go ahead and draw out. One of these functional groups is a carboxylic acid. There's that new carbon-carbon bond you might have made over here by hydrolyzing. And I'm going to draw this other functional group, this other carboxylic acid you generate in this flipped around form. And this will allow us to see mechanistically what's going on. I'm not going to draw the 6-step mechanism for hydrolysis of both of these esters. You already know that mechanism. We've covered that backwards and forwards, literally, with Fischer esterification and acid catalyzed hydrolysis. Whenever you have a carboxylic acid next to a ketone, next to an amide, that would be hydrolyzed under these conditions. Next to a carboxylic acid, in theory next to an aldehyde. When you heat these under these acidic conditions, it spontaneously loses carbon dioxide through this arrow pushing mechanism that I'm showing you here. And so you lose CO2 when you do that. And it generates an enol at this position. If you follow my arrow pushing, I'm going to end up with an OH here and a double bond. And that enol then tautomerizes to the keto form, to the carbonyl. I'm not showing all the steps in this mechanism. It's many steps, like 6 steps to hydrolyze each ester and then more steps here. But the point is, you have to look, whenever you're heating in acid, carbonyl compounds that have carboxylic acids, where the carbonyls are at the beta position to each other, those are susceptible to loss of CO2. Now, so you can see that if you didn't want 2 dicarbonyls next to each other, when you use this acid hydrolysis procedure, you lose an ester and the carboxy group on there. Now we don't need to do this nowadays. Nowadays, because we have LDA, if I wanted to form this carbon-carbon bond right here, I'll put a dot right there in that carbon-carbon bond. If I wanted to form that carbon-carbon bond, nowadays we do things much more simply. We use lithium diisopropylamide. So for example, if I had this compound and I wanted to form a carbon-carbon bond, nowadays we use LDA to make the enolate, and our recipe is lithium diisopropylamide, THF, minus 78 degrees Celsius. And then step 2, we throw in our alkylating agent, like methyl iodide. And then we form the carbon-carbon bond. And if we wanted the carboxylic acid, you generally don't. Generally, you want to reduce that with dibal H or add in Grignard agents. But if you wanted to convert this to the carboxylic acid, then we could simply hydrolyze that using either a one-step acidic hydrolysis or saponification and then treatment with acid. I'm going to draw the one-step hydrolysis reaction. HCl, water, and then you boil it at 100 degrees, or I'll just write the delta symbol there. I'll allow you to do that. This is what we would do nowadays to make that carbon-carbon. We wouldn't start with a 1,3-dicarbonyl compound. So in this case, there's really not a benefit to doing this old-style 1960s chemistry. But the book teaches this to you in this section 23.9. And sorry, this ester is an ester of a compound called malonic acid. When you have these two carbonyls, that's the ethyl ester of malonic acid, or that compound would be called diethyl malonate. Now, I mentioned that it doesn't have to be a 1,3-diester. You can also have beta-ketoesters. So let's try to imagine what it would be like if we had, for example, a ketone with an ester next to that. Then, so let's try to imagine a situation where maybe we've taken a beta-ketoester. So there's the ketone group, that's the alpha position, that's the beta position relative to this ester. And let's suppose we deprotonate this with sodium ethoxide. And it's really important not to use sodium hydroxide to deprotonate here at this alphabet. What would happen if you added sodium hydroxide? Well, you'd cleave your ester, and then the carboxylic acid would react with the sodium hydroxide, and you'd end up losing it. So if you use a base, your alkoxide base has to match the ester, and I'll come back and talk about that more later. So in this case, if we wanted to add an ethyl group to this, we'd treat it with sodium ethoxide and trap with ethyl iodide. And if we wanted to add another alkyl group here, right, we still have a CH, we could do that again. So let's see how we would repeat that. Replace that other H with another alkyl group. We had sodium ethoxide to deprotonate. Again, you don't need LDA when there's two carbonyls with a 1,3 relationship to each other. So then we throw in our alkylating agent, for example, methyl iodide. And that alkyl group would still be there, the ethyl. And then there's our methyl group that we just added. And we don't have any more protons left to deprotonate here, so we can't add any more alkyl groups. And now we can use those same conditions that we used when there was two esters next to each other. Hydrochloric acid, water, and you boil it. You boil it overnight. And you not only do you hydrolyze this ester, but it also pops off carbon dioxide. And so what you end up with is this. And initially it generates an enol under the conditions of the reaction, and that enol gets protonated. Let me finish drawing my ethyl group here. This turns out to be a stereogenic center, so let me go ahead and indicate that you get a mixture of stereogenic centers. No matter what you start with here, when you deprotonate and make a planar enolate, you can't control whether the methyl group comes in from the top or the bottom. I could have drawn the methyl with a wedge, I could draw the ethyl group with a wedge, just something to indicate there's a stereogenic center there. I'll write plus E, and then over here I'll write plus E. But I could have drawn the methyl with a wedge. I'll go ahead and draw the other stereogenic center here. Maybe it makes more sense to me if I have an alkyl chain to draw one of the groups wedged and one of them dashed. All right, so there's a kind of a slight circumstance. I'm not sure if that's the right terminology here. There's one obscure place where this might be a valuable procedure, where you could do something that you can't do with LDA. And so let me just remind you that after you lose that extra carboxy group, let's suppose I wanted to do that with LDA. That's not so easy. So in other words, if I start with this ethyl group over here, like this, and I try to treat that with LDA to do the same, to make this same compound, I'm going to run into problems because, remember, LDA is super choosy and super selective for the less hindered side. If I have a ketone that's about equally acidic on both sides here, LDA will go after the least hindered side. So when I use my recipe of LDA and THF and minus 78 degrees Celsius, I'm not going to deprotonate over here, even if I wanted to. The LDA will selectively pick the proton off of the less hindered side. And so I could draw the enolate with the CC double bond. I'm going to draw the enolate in this resonance depiction here. Right, that's the lithium, there's a lithium counterion there that gets generated. And then when you treat this with methyl iodide, you don't add the methyl group to the same side as we did with this this is called the acetoacetic ester synthesis up above. Let me, you add the methyl group over here on the less hindered side because that's where the enolate was. And so you don't get the same product with LDA because LDA deprotonates on the less hindered side. Whereas in this case, you deprotonate the most acidic proton. Even if you used LDA on this side, it would still go after the more acidic proton. The reason why LDA is choosy here is because both sides are equally acidic. Now this class of compounds, this compound here, this is called the acetoacetic ester synthesis because this compound is called acetoacetic acid. And so this general synthetic strategy for making substituted ketones comes from the fact that you start with this substance called acetoacetic acid. I'm not able to draw that in very small, but that's acetoacetic acid. Okay, so again, sometimes LDA doesn't give you what you want, and you can't force it to deprotonate on the more hindered side. It's always going to deprotonate on the less hindered side. We have ways around this in modern organic synthesis that doesn't require us to use the acetoacetic ester synthesis, but it's kind of a cool historical reaction, and the book seems to have a lot of these historical types of reactions in there. Let's have a major switch in gears here. We're done with chapter 23, and let's go ahead and enter a new chapter where we're making enolates. Sometimes we're making those enolates using somewhat weak bases. Sometimes we're making those enolates using very powerful bases like LDA, but instead of doing SN2 reactions with those enolates, which are just amazing carbon nucleophiles, we're using those enolates to attack carbonyls. Well, that just sounds like modern organic chemistry to me, is using enolates to attack carbonyls. So let's talk about that. That's chapter 24, right there. That is chapter 24. Remember in chapter 23, we made enolates and used them for SN2 reactions. And now in chapter 24, we're making enolates and we're using them to attack carbonyls. That just feels so good, sounds so good. Everything about that sounds good. All right, I'll switch to a brown pen color because that just, to emphasize the fact that we're starting a new chapter here. All right, let's go into this. So in this chapter here, just give me a minute here to get things ready. So chapter 24 is about making enolates and having those enolates attack carbonyls. And when we do that, we're going to make carbon-carbon bonds. But we're going to generate a lot of stereogenic centers with this process. So there's going to be a lot to pay attention to when we talk about stereochemistry. The mechanism for the reaction that we're going to be going through, so when you take two aldehydes, this process of making enolates and using them to attack carbonyls falls under a general category called the Aldol reaction. Kind of sounds like aldehyde kind of sounds like alcohol, so you kind of get the name aldol. So sometimes we don't use aldehydes, we use other things, but this is the origin of the reaction. And the key functional group we're looking for are beta-hydroxyaldehydes. So here's the aldehyde, and here's the alpha position, and here's the beta position. And at that beta position, we have a hydroxy group. Whenever you see that pattern, that tells me I can make that with an aldol reaction. Let's go ahead and take a look at the mechanism for this process. So I'll start by drawing out an aldehyde. And let me recognize the fact that there's a proton here. Aldehydes are about 100 times more acidic than comparable ketones, than similarly substituted ketones. And you'll notice they're using sodium hydroxide here. You don't have to worry about hydrolyzing any esters here. Now, I didn't talk about the hydroxide catalyzed mechanism for hydration of carbonyls, because when you put in hydroxides with sodium hydroxide with ketones or aldehydes, you're not thinking about hydrate formation. You're going to get aldol reactions and carbon-carbon bond forming processes occurring. So in these cases we have, sorry, let me use I meant to use my brown pen again. We've got hydroxide anion floating around in there, and let me go ahead and draw out what we're heading towards here. I'm not going, when I draw out the arrow pushing mechanism, I'm not going to worry about the stereochemistry when I do this, when I depict the arrow pushing mechanism. I just want to focus on how do we explain using arrow pushing where that new carbon-carbon bond comes from. So we're going to start off this process by deprotonating the proton, and I'm going to leave the electrons right here in the alpha carbon, because that will remind me what part is going to be nucleophilic. So when we do that, we generate an enolate. Here's the enolate. There's still a proton there, but I'm not drawing that proton. And we generate water as a byproduct. I'm not going to show the arrow pushing, but I'll just write that you could also have drawn the arrow pushing where you push these electrons from the HC bond all the way to the carbonyl and push and break the CO pi bond, and that would generate a different depiction of the enolate. And if you wanted to depict it in that way, that's okay too, right? These are resonance structures of each other. So you could have done your arrow pushing to generate this resonance depiction, and that's fine too. But you know, as we're just starting to learn the aldol reaction, I kind of like to see that carbanion there, because I feel like maybe that'll be more intuitive to you. And as soon as this collides with another aldehyde molecule, aldehydes are super electrophilic. It's so easy to attack aldehydes. They're way more reactive than ketones. Well, they're more reactive than ketones, which are way more reactive than esters, and way more reactive than amides. So it's so easy to add to aldehydes. Boy, as soon as I see some sort of a carbanion nucleophile, I just want to add to a carbonyl, right? And in these reaction conditions, you don't form 100% enolate. When you deprotonate at equilibrium, only about 1 out of 100 of your aldehyde molecules are deprotonated, because this is reversible. So 1 out of every 100 of these is deprotonated, so it's easy to collide with a neutral aldehyde and form a carbon-carbon bond. And that process is so important, that process of forming a carbon-carbon bond by adding to a carbonyl group. Remember all of chapter 20 on Grignard reagents and alkylithium reagents, it was all addition to carbonyl groups to make carbon-carbon bonds. So we generate this alkoxide anion intermediate, and then we still have in our solution here our protonated base, which in this case was sodium hydroxide. And so we're simply going to regenerate our hydroxide base by deprotonating that. And if you wanted to draw for the arrow pushing mechanism, you could have drawn B here. I'm just drawing the specific reaction conditions. Okay, so this is the transformation. This is the aldol reaction up here, and here's the 3-step mechanism for that aldol reaction. Right? I think there was some point in your distant past where you learned about SN2 reactions, but that's not really how chemists make bonds. We've covered so many zillions of more reactions this quarter, and it seems like almost every one of those reactions we learned this quarter is more important than an SN2 process. Now, whenever chemists, the aldol reaction is so embedded in the mindset of synthetic organic chemists that whenever we see this pattern, we always look for this pattern of carbonyl group and then beta to that carbonyl group and oxygen. Because we know in that circumstance that we could have made this bond through an aldol reaction by having an enolate attack a carbonyl. And so let me show you, here's an example of a super potent anti-cancer natural product that was isolated from a marine sponge called spongistatin. Two different groups isolated this potent anti-cancer compound, active at femtomolar activities. It's just, you cannot go into the laboratory and invent things that are this potent. So some marine sponge is clearly trying to survive by generating super toxic compounds. These compounds happen to be super toxic towards cancer cells. And synthetic chemists have figured out a way to make this. And when you look at this as a synthetic organic chemist, it's hard to miss, you can't miss this fact that everywhere you look in here, there's carbonyl group. Here's the alpha position. And look at the beta position right there. There's an oxygen. You could have synthesized this bond here, maybe I'll try to make it in blue, using an aldol process. And if that was derived by reduction of some carbonyl to an alcohol, you could have derived this bond through an aldol. Everywhere you see 1,3-dioxygenation patterns, because it's easy to reduce this, right? It's easy to reduce this. I'll write a reduction symbol here. It's easy to reduce this to a pattern where you have oxygens kind of 1,3 to each other here. So wherever you see that pattern, those bonds can be synthesized through an aldol process, either this, depending on which side was the aldehyde. And so that's how this molecule was synthesized in the laboratory by synthetic organic chemists, by doing one aldol reaction after another aldol reaction after another aldol reaction. And you can see here in their synthetic plan that they're making esters. From chemistry, you know how to do. Here's a bond they made using a Wittig reaction. You know how to make Wittig reagents. You know how to deprotonate those with LDA, with lithium or strong bases. And you know, in this chapter, we're going to talk about aldol processes. And that's how you can synthesize anti-cancer. And by the way, why don't they just get more of these sponges out of nature? You will not be able to dive deep down into the ocean and find enough of these sponges to cure many patients. These, if you want to get your hands on any quantities of these, it has to be made synthetically. And generally, synthetic chemists will design simpler analogs once they know the structure of the anti-cancer agent. But you have to start by coming up with a synthetic group, because you just can't dive and get enough sponges. You probably I don't think it's that easy to identify the sponges that produce these when you're swimming or you're diving around in the ocean floor. And if you gathered them all, they'd go extinct, I'm sure. Okay, let's go ahead and keep going on this aldol process. It's super common in organic chemistry, making enolates and using them to attack aldehydes. Now there's two possible fates to the aldol reaction, or two sequential fates to the aldol reaction. Initially, when you do an aldol reaction, if I just take acetaldehyde, you don't have to draw two molecules of acetaldehyde, because if I just draw one molecule of acetaldehyde and I draw a chemical transformation with reagents, it is understood that you're not running the reaction on one molecule. No synthetic chemist runs a reaction on one molecule. There's usually 6.02 times 10 to the 23rd molecule, so I don't have to draw this second equivalent, but I've just done this here so you can see the pattern. You could write two equivalents if you're trying to pay attention to stoichiometry. But the initial product of this reaction is the aldol product, where we've generated a new carbon-carbon bond. So let me just put a little squiggly here. That's the new carbon-carbon bond. I'll write new. That's the new bond. Sometimes, depending on the substitution pattern or depending on the conditions, you eliminate the elements of water. So there's two H's here. I'm going to draw one of them. And when you heat these aldol reactions, it tends to favor an elimination process. When you're heating in the presence of base, it tends to favor the loss of H2O. I'm going to draw that here. Generally, we don't draw inorganic byproducts like salts or water, but just so you can see what got lost here. We lost the H and we lost the OH, and we generated a double bond. And this pattern of enone, alpha-beta unsaturated carbonyls, is super indicative that you could have made this bond right here through an aldol reaction. That bond right there just screams at me, aldol chemistry, aldol reaction. So this process of taking aldehydes or carbonyl compounds that have acidic H's next to the carbonyl group, they're acidified by the carbonyl, and treating those with base under heating conditions to generate enones, we refer to that as an aldol condensation. You've lost water. That's what condensation implies when you say condensation reaction. Now, one of the problems with this reaction is we don't have control over stereochemistry. You're going to end up with a mixture of E plus Z. So this is the E or trans isomer entgegen in German, and you also get the Z isomer, which I didn't draw, the cis double bond with stereochemistry, and you cannot control that. You get a mixture of E and Z. So that's one of the less satisfying aspects to this reaction, is getting a mixture of cis and trans isomers. And I'd like you to indicate that. I ask you on my exams, clearly indicate stereochemistry and the presence of stereoisomers, if any. R and S are one type of configurational stereochemistry. E and Z are a type of stereochemistry that doesn't involve stereogenic centers, but it is a stereochemistry. And those two compounds would have completely different properties. If I went back to that spongistatin anti-tumor molecule and I flipped one of the bonds from E to Z, it wouldn't be active anymore. It wouldn't have the same properties. Let's go and talk about this elimination mechanism. This elimination process where we take this aldol intermediate that dehydrates under the basic heating conditions of the reaction. What's going on there? It's not an elimination mechanism you've seen before. It's actually the most common elimination mechanism, and for some reason, they decided not to teach that to you in the beginning of our organic chemistry sequence. It just doesn't make sense to me. So if you have this aldol product floating around in the presence of base, these protons that are right here next to the carbonyl are just as acidic as they were the first time you pulled off a proton from acetaldehyde. They're just as acidic. So if this is floating around in sodium hydroxide, it's getting deprotonated just like acetaldehyde would get deprotonated. And so the hydroxide anion that's present under these conditions, let me just symbolize this as a base. We don't actually care what the basic species is that's pulling the proton off. I'll put a minus charge here because I'm using it as a symbol for hydroxide anion, but if you wrote it as neutral B, just keep track of your charges as you make conjugate acids from this or use it as a base. So let's go ahead and draw out the arrow pushing for this. If I deprotonate here, right, I'll leave the electrons here at this alpha position, and we'll draw out the enolate intermediate. And so there's this deprotonation, it's reversible that's occurring. I'll make that lone pair nice and big. Boy, when you have nucleophilic lone pairs on an atom that's next to an alcohol, those will push out the hydroxide. It will push out the hydroxide, and the hydroxide will act as a leaving group. Let's go ahead and draw that out, and you need to be comfortable with this. Look at that. That is so, you couldn't stop that carbanion from pushing out the hydroxide. It's so easy. You might be saying, well, Dave, I don't remember that. I thought I was told that you can never ever use hydroxide as a leaving group. I thought I was told that you can never use alkoxides as leaving groups. Ethoxide, TB, of course you can. You can't use them as leaving groups in crummy SN2 reactions. That's because SN2 reactions are crummy. But when you've got an O minus or an N minus or a carbanion minus next door, they have no problem pushing out hydroxide or ethoxide or any alkoxide leaving group. Don't take some rule from SN2 reactions when that was the only reaction you knew and apply it to the rest of organic chemistry. No problem. Right? That's acting as a leaving group there. So I hope you didn't make up some list of leaving groups and put it in your brain, because leaving group, just means something left. There's no, it depends on how powerful your nucleophile is, and this is right there all the time, pushing out that leaving group. Now, you're going to have a hard time getting used to this. You never saw anything like this back in the first quarter of your organic chemistry sequence. You didn't see this in the second quarter of your organic chemistry sequence. This whole process of using anions, O minus, N minus, to push out hydroxide or alkoxide leaving groups is all from this quarter. And you have to get used to this. This is the most common elimination mechanism, not E1, not E2. But because you're going to have a hard time, adjusting to this new elimination mechanism, you're going to make this mistake. And then I'm going to tell you, I told you don't make that mistake, but you're going to make it anyway. So let me just tell you what you're going to do when you panic on the exam and you're running out of time because you didn't practice enough problems in the book or in the sapling homework. And here's what you're going to have a tendency to do. You're going to have a tendency to write out this elimination mechanism as a concerted E2. I don't want to write regular arrows because it kills me to write this out. This is so utterly impossible. You're going to try to write it out all simultaneously happening, like an E2 elimination. Let me tell you when this is going to be an E2 mechanism like I've shown below. It will never be E2. Never, ever. Never, ever a one-step E2 elimination mechanism. If you pull the proton off, the electrons go to the carbonyl, not to the antibonding orbital of the OH bond. You make an enolate. So I've drawn the electrons sitting here on the carbon, but they're actually donating into the carbonyl group to make a double-bonded enolate structure. Don't ever, ever write this out as a concerted E2 elimination mechanism. If you do, I will immediately count it wrong, and then I'll say, remember, I told you don't do that. Remember, I told you don't do that. Even though I know it's hard for you not to do that. It's just hard to adjust. Again, you've had an academic year, a full academic year to get one-step E2 elimination mechanisms into your brain. And we've only had weeks, maybe you got a month left in the organic chemistry sequence to adjust to this base mechanism. Oh, I forgot to give you the name for that. This two-step mechanism for elimination is not E1, it's not E2. We call it the E1 conjugate base mechanism. You start by generating some anion, a conjugate base of what you started with, and the lone pair on the conjugate base pushes out the hydroxy group. Or you could have drawn it as an enolate with a CC double bond, but again, something nucleophilic is pushing out the leaving group. You generate an anion, and then the anion pushes out the leaving group. That's the E1 conjugate base mechanism. That's the most common mechanism for elimination in organic chemistry. Way more common than E2. And I'm sorry we didn't teach you that 7 months ago. That's too bad. That's, again, I understand why you're going to make a mistake on that, and I'm just going to have to tell you, try not to make that mistake. Okay, I need to resolve this issue of how do you know whether you're going to be able to stop at the alcohol stage or eliminate water to give the enone. And I'm going to give you clear instructions, whereas the textbook does not give you clear instructions on how to predict what's going to happen. Generally, for any organic chemistry reactions, whether you're trying to decide between SN1 and E1 or SN2 and E2, heat favors the elimination pathway. Heat favors elimination. So if you want to clearly indicate to me that that you're eliminating, like instead of if you just want to do an aldol reaction, then I'll tell you to just add a base. It could, in this case, you don't have anything that can hydrolyze like an ester, so you're free to use sodium hydroxide. Or in reality, that's not very soluble in organic solvents, so we would probably use sodium ethoxide or a soluble base that's more soluble. But this is fine. The product of this reaction, and you can, if you follow the stoichiometry, it's actually catalytic in sodium hydroxide. You can draw this out. Don't worry about the stereochemistry right now. But the product of this would be the beta-hydroxycarbonyl. If you want to indicate conditions that will favor the elimination, where this goes further to eliminate, then I want you to write a delta symbol or spell out the word heat. Heat will favor eliminate. That's how you indicate to me that you're trying to run the reaction under conditions where you favor heat. If I draw a delta symbol, I want you to draw the loss of water, the condensation product. Whereas if I just draw the base, like sodium hydroxide or ethoxide or isopropoxide or t-butoxide, and without heat, then I want you to draw the aldol product with an alcohol OH group at the beta position. And the book was never clear about how to tell whether, but I'll give you one case where you don't need to heat it and it's going to spontaneously eliminate whether you want it to or not. And here's that case. So the case would be if you had a chance for conjugation on the product of the reaction. So let me go ahead and draw out a case where we'll go ahead and take an example of two ketones. And when you treat this with sodium hydroxide with no heat, so I'll just try, let me just indicate that. I'll use it in cool blue, no heat, just room temperature. You can't stop this product from eliminating. And let me explain to you why that is. Boy, I wish I'd left a little bit more room here. And this will go all the way to the elimination product. Because whenever you have a chance to generate a product that is conjugated, let me draw the phenyl group here. There's conjugation between this new double bond and the benzene ring. You can't stop the elimination process from occurring. So if the new CC double bond that you generate is conjugated, there's now conjugation between this new double bond and this phenyl group that's over here. There's conjugation there. You just have to assume that you're not going to be able to isolate this under the basic conditions of the reaction. Just assume it spontaneously eliminates even if you don't draw heat. You can still draw heat, but if I don't draw heat, you have to draw the condensation product where you've eliminated water. So, whereas up here, you have if you don't write heat, it's going to stop here at the aldol alcohol stage. Okay, so I'm trying to give you some clarity there on how you should indicate whether your conditions are going to favor elimination or just stopping at the aldol addition stage. I'm trying to watch the time here because I went a bit over last time in the lecture. I don't have a clock here. It's got so many screens that I'm staring at. Okay, so you've got to master this aldol process. It's something you've got to work problems backwards, synthetically, going forwards, backwards, every which way. So let's go ahead and talk about what are some cases where you won't get aldol reactions, where you can't get an aldol reaction. Maybe this is completely obvious, but if I take a substrate that looks like this, that can't undergo aldol reactions, right? If I take a whole flask full of zillions of molecules, let me draw another molecule just like that, except I'll draw the chemical structure. You can't do aldol reactions on benzaldehyde by forming a bond here at this position. You can't form any. We can do aldol reactions where we attack benzaldehyde, but we can't form enolates. You can't just simply mix benzaldehyde together and get any aldol reactions to occur. So, right, if we have to have things that have alpha CHs, and there's no alpha CHs here. So even if you treat this with sodium hydroxide, you won't get any aldol process occurring. Right? We've got to have something that has CHs at the alpha position. I showed you on the last slide that in theory you can take ketones and do aldol reactions. There's other conditions for doing aldol reactions with ketones, but you can get these to work with base to some extent. So if you take acetone, I've drawn two molecules of acetone. One of them I tipped on its side here. It's just imagine a flask full of acetone. I could have drawn it like this and written 2 to indicate 2 if I were trying to keep track of stoichiometry. So if you treat this with sodium hydroxide and heat, those are conditions for an aldol condensation. And the pattern that you need to get used to is you draw a carbonyl and you draw a double bond, right? Where that other, it's kind of like recognizing a Wittig reaction. You need to master that pattern recognition, just like you master pattern recognition for a Wittig reaction. Boy, as soon as I see a alpha beta unsaturated carbonyl, I'm thinking backwards. I'm automatically thinking backwards. That's like, wow, I could have made this CC double bond from an aldol, and let me draw that out. You need to be good at that. If I draw an alpha beta unsaturated ketone for you, or alpha beta unsaturated ester or carbonyl, I expect you to know how to make that using an aldol type process. So you need to practice that. And the reason why this works because there's CHs here. If you don't have those CHs, you can't really do aldol condensation reactions. I'm going to try to put these two pieces together because I'm telling you, aldehydes don't have CHs, so they can't, they can't form enolates, whereas ketones, they're not quite as easy to attack. The aldol reactions work best when you're attacking aldehydes because aldehydes are substantially more reactive than ketones, substantially easier to attack than ketones. Let me come back to this concept this idea that you need to recognize how you can make enones, alpha beta unsaturated enones, through aldol reactions. So if I show you the structure of an enone, I expect you to know what pieces you would need to mix together to do an aldol condensation to make that. So look at this enone situation here. I expect you to know how to make that using an aldol condensation. Watch this. I expect you to know that I could have deprotonated some ketone to make an enolate, and I could have condensed it with another carbonyl that just happens to be the same, cyclohexanone. If you just take cyclohexanone and treat it with sodium hydroxide and heat, you'll get this enone. There's better yielding procedures than this, but this is the way in our course that I expect you to show how you would do an aldol condensation to make this enone. Here's another one. This is a little more tricky because it's got a ring. I find that rings really trip people up. What substrate would you need to take, or substrates would you need to take in order to make this double bond? Well, let me start by drawing everything but that double bond. There's the alpha position. That's where we would make deprotonate to make enolates. And here's the rest of that piece. And if I'm following this pattern through, then I need to write a carbonyl right here. Right? You deprotonate and make the enolate, it attacks intramolecularly, then it makes another enolate, eliminates that whole business. This would be the substrate. And I expect you to be able to work backwards and say, oh yeah, I could take that dicarbonyl compound and do an intramolecular aldol condensation. So easy here. And notice, I could write delta, but because the double bond is conjugated, I don't have to write the delta there. You could, but probably this would work at room temperature. Okay, here's a hydroxycarbonyl compound. And I expect you to know that you can make this bond right here by having aldol reactions occur. Let's go ahead and take a look at what pieces would be required for that. And this is kind of the way it is. Generally when we draw molecules out, the bonds get flipped around and twisted around, so it's not easy for you to see necessarily that these two pieces would have been the same. So over here, I would have had an aldehyde, and here's that ethyl group there that gets converted into an enolate. And then over here, I would have another aldehyde that gets attacked. And it turns out that these are the same molecule. So I don't even have to write two of the same molecule. I mean, there's 6.02 times 10 to the 23rd molecules. We don't draw all of them out. If you were, for some reason, trying to indicate stoichiometry, you could write the number 2 next to one of these, or write 2 of them. That's a little weird to write. Well, maybe it's not weird here, but I expect you to be able to work backwards. When I show you a product that can clearly be made through an aldol condensation, I expect you to recognize the bond that you can make, and then to figure out what pieces you would make. There's the new bond right there. Here's the new bond right here. I expect you to recognize that, and you have to practice. And no matter, I'm not going to draw it in some simple way. I'm going to flip it around, not because I'm a jerk, but because oftentimes when you see molecules, they just happen to be drawn in some way that fits on the page or looks nicely arranged. And sometimes those nice arrangements don't make it easy to see how to work backwards to the starting materials. I'm going to go ahead and stop right there, and this whole chapter, make enolates and attack carbonyl compounds. That's what we're doing in this chapter. And you can either stop at the aldol stage, unless there's some conjugation thing going on. Or if you add heat, you can drive it all the way to the enone, so it does a spontaneous dehydration under the conditions of the reaction. That's the aldol addition reaction and the aldol condensation reaction. That's our chapter here. So get ready to see lots of compounds that have enones in them, these alpha beta unsaturated enones. And thanks for coming to lecture. Keep working problems, keep going to discussion section, keep staying engaged with the material. And I'll see you guys on Wednesday.